Okay guys, in this video this is our third video on circuits, and here we're going to be thinking about the RC circuit. It's called an RC circuit because it contains both a resistor R and a capacitor C. So here this is a multi-loop circuit, as you can see, and I've got the battery over here and I have a switch here, and what that's going to allow me to do is to either include the battery by closing the switch. If the switch is in the closed position, then the battery is included in the circuit, and we would have this outer loop would be the travel of the current. And then if I were to open the switch, as you see it in the current configuration, then the circuit here would just include the capacitor and the resistor. So maybe let's start by thinking about what would happen, and we will ultimately be doing a little bit of math here, but let's think about the situation where the capacitor is uncharged and the switch is put to the closed position. And this will lead to what we will call charging the capacitor. So the capacitor is uncharged, and then I close the switch so that the battery is included in the circuit, and if I do that, then we're going to be charging the capacitor. So the battery will charge the capacitor. And just so maybe I'll go ahead and make that clear in terms of the picture. So what I'm saying here is that this is going to be closed. So charge can now flow. We're going to have current. The current, again, we're thinking about conventional positive current, will go this way and then this way, leading to positive charges accumulating on one side of the capacitor. The positive charges will flee from this side of the capacitor, leaving that with a negative charge. And so then we have a positive current going this way back to the battery terminal, the negative terminal of the battery, positive and negative. And so what we're going to get here, if we zoom in on the capacitor, is we're going to have a situation where the capacitor is going to have an electric field here. It's in the direction of that electric field would be in this direction, right? As the capacitor charges, we're going to get an electric field. Now, the capacitor will, of course, or the current will continue to flow. As shown, the current will continue to flow through this circuit until this capacitor is charged up such that the potential difference across the capacitor is equal to the EMF of the battery. So I could put in like a voltmeter here. A voltmeter is just a handy-dandy device that allows us to measure the voltage difference between 2 points, the change in voltage. And if I were to take this voltmeter and connect it across the capacitor, there will be current until the delta V here is equal to the EMF of the battery. And once the delta V across the capacitor is equal to the EMF of the battery, then the current would be zero. So, in other words, maybe it would be helpful to think about this in terms of a graph. If I were to graph the current, we could wonder, like if I were to graph the current as a function of time, what would it look like? Well, initially, if we think about the initial time equals zero, where there's no charge on the capacitor, that would mean, in a sense, the capacitor would look like just a wire, in the sense that there would be no back EMF. There's no potential difference across the capacitor to oppose the EMF of the battery. So we would expect that like the initial current here would just be, from Ohm's law, would just be E over R. That's just Ohm's law. We remember that, so I'll just put this up here. We know that the I is equal to V over R. And since there is no voltage in the capacitor, then the potential difference in the circuit is just the EMF of the battery. However, as that capacitor gains charge, it will gain an electric field, and as it gains the electric field, it will gain a potential difference. So now there's going to be an EMF here. You're going to start to get a voltage here and an EMF due to the capacitor, which is opposite the direction of the EMF of the battery. What does that mean? That means that as the capacitor charges, the total voltage drop across the resistor, so if I now imagine putting a voltmeter here, the total voltage drop across the resistor is going to decrease, because there's going to be, if we think about from the perspective of the loop rule, and we will do this later, if you imagine a positive charge that gains a certain potential as it traverses the battery, it is going to lose some of that potential as it goes across the capacitor. And so there's less energy left as it traverses the resistor. And so what we're going to see here is that as time wears on, the total voltage drop across the resistor is going to decrease, and so the current through the resistor is going to decrease. And so we're going to have this situation where there's a current, but as the current flows, that current creates a back EMF, and that back EMF is going to decrease the potential, which then decreases the current. And you might kind of get a sense of what the shape of this curve will be, that it's going to sort of be like an exponential decay going asymptotically towards zero at t equals infinity. We're going to prove that a little bit later on, but you might kind of get that sense. And again, just to kind of reiterate the intuition on this, initially the potential throughout the circuit is just the potential of the battery, but as time wears on, as the current flows, the total EMF of the battery diminishes as you get a back EMF from the capacitor. And so as the total EMF diminishes, the current diminishes. And since there's a relationship between the current at any given point in time and that back EMF, you get a sense that there might be an exponential function in here. And we'll see that there is indeed. All right, so let's come up with an expression, maybe a mathematical expression for, or see if we can derive a mathematical expression for this curve. And to do that, I'm going to use the loop rule. So I'm going to start, maybe I'll start at this position right here, and I'll traverse as we were, or I'll go through the circuit as we were kind of talking before in this sort of counterclockwise direction. So I would get, the loop rule would give me E, so I gain the EMF of the battery, minus the voltage of the capacitor. And just to remember what that relationship is, just remember that, put this up here, that C equals Q over V, which means V equals Q over C. So that means the voltage drop across the resistor is going to be Q over C. Maybe I'll use little q. Q over C. And then the voltage drop across the resistor is I times R. And then to close the loop, this whole thing has to equal zero. So this is just Kirchhoff's loop rule. And you might look at this equation and say, all right, well, how the heck are we going to solve it? And to indicate how we're going to solve it, I might just remind you that there's a relationship between Q and I. So I've got Q and I, and we remember, I hope, that the definition of I is dQ dt. And so what you can see here, or what you might be seeing here, is that we're going to end up with a differential equation, because I could rewrite this as E minus Q over C minus dQ dt times R equals zero. So I have a function here, Q, right? Q is changing with time. Remember what Q is. Q is the charge on the capacitor. That is changing with time. But in the same equation, I have Q and I have its derivative, I, or dQ dt. And, you know, when we get these sorts of differential equations, we often do indeed expect to have an exponential function. And as we will see that there is one here. So from here to solve it, the first thing I'm going to do, and it won't necessarily be clear to you yet why I'm doing this, but I'm going to multiply both sides of this equation by the capacitance C, and that's going to give me EC, that's going to give me EC minus Q minus dQ dt times RC equals zero. And now I'm going to add dQ dt RC to both sides, and I'm going to get E, or maybe I'll do it this way. I'm going to put dQ dt times RC equals EC minus Q, like so. And then I think what I'll do is I'm going to try to get the right-hand side is the term that's got the Q in it. So I want that with the DQ. So maybe I'll write this. What if I change this to DQ over EC minus Q equals DT over RC? I think that's right. And now I'm at the point where I've separated the variables and I've gotten the variable of integration on the right side. And so now I integrate, and I'm going to integrate here both sides of the equation. And the right side, this R and C are just constants, but I'm integrating from time equals 0 to some future time t. And then I'm going to, on the left-hand side, I'm going to integrate from Q naught to Q. And here, I'll put that as lower Q. But I might note that Q naught, since I started with a capacitor that had no charge on it, Q naught here is just 0. So I might just go ahead and substitute in a 0 in this particular case because the initial charge on the capacitor was 0. Maybe it's easiest just to immediately deal with the right-hand side. The antiderivative of dt is just t, so this is going to be t over RC on the right-hand side. And then on the left-hand side, I'm just going to have to do a u sub. I'm going to let u equal EC minus Q, and then du is going to be negative dq, which means in order to get this into the form I want, I need to have a negative up here. And to have a negative up here, I need to throw a negative in front over there. So there's this whole term on the right-hand side should have been negative or needs to be negative in order to have this in the right form. So then I just get the antiderivative of 1 over u, which is natural log of u. So this is going to turn into the natural log of EC minus Q, evaluated from Q equals 0 to Q. Using logarithm rules, this is just going to turn into the natural log of EC minus Q over EC equals negative t over RC. And from here, it's algebra. I'm going to exponentiate both sides. I say EC minus Q all times EC equals e to the negative t over RC. There's our exponential term. We knew that we were going to get this sort of exponential term, or we expected it. Multiply both sides by EC. And now solve for Q. So I have to subtract EC from both sides and multiply through by negative 1. And I'm going to get Q equals, what is this going to be? EC minus EC times e to the negative t over RC, which I could write this way. Factor out the EC, 1 minus e to the negative t over RC. And this now is our final expression. This is Q on the capacitor, the charge on the capacitor as a function of t. Q as a function of t. And we see that it does have this exponential form. Now, this is not an exponential decay equation. This is an exponential approach equation. But remember, what's happening here is the charge Q is exponentially approaching the fully charged state. So the graph I'd made before was the current as a function of time. So if I had instead graphed the charge on the capacitor as a function of time, which maybe I should have done, we would have then an exponential approach situation. The initial charge on the capacitor would be 0, and then it would initially, the capacitor would charge up very, very fast because the current was large because there's no back EMF from the capacitor. But as the potential difference across the capacitor increases, the rate of, or the current flow would decrease, and as the current decreased, the rate at which the charge accumulated would decrease as well. So you'd have this concave down exponential approach situation. And this point right here, that what is exponentially approaching is the final charge on the capacitor, which is the EMF of the battery multiplied by the capacitance. That's EC. that was this term down here. So if we were to go back down here, this it will be the final charge. If you let t go to infinity, then this whole thing is just, this whole term right here is just going to turn into 1. And so t at infinity is EC. So that's our exponential approach equation. Now, if you took the derivative of this thing with respect to time, then you would get an equation that would be in the form of an exponential decay equation. Because that would, if you took the derivative of this, the derivative of dq dt, we already said was, or is the current. That's the current. So you would get I, you get an expression of I as a function of time. And that would have the form of the initial current, that's E over R, times e to the negative, and it would be the exact same term, t over RC. So this would be an exponential approach equation. So what this equation says is when t is 0, this whole thing is just 1. So initially, the current is E over R, because again, when the capacitor is uncharged, it behaves just like a wire. And then as t gets bigger and bigger and bigger and bigger, the current goes to 0. So this would be the exponential decay equation right here. Exponential decay. And that would be this curve, this first curve that we had derived, or that we had sort of guessed at, hinted at here. All right, so now I think what I'd like to do is think a little bit about the sort of the situation where, what if we now had the capacitor all charged up, and then we opened that switch. So remember, the switch was here, right there. There was a switch, and what if I went ahead now and I opened that switch? So now we have the fully charged capacitor. We've waited a long time, and we've given this capacitor an initial charge. So I'm going to say that the charge on the capacitor is, maybe I'll do it over here in blue. I'll say Q naught on the capacitor is E over C, right? That capacitor is fully charged up. And now I open the switch, and now what's going to happen is we're going to have a situation where, because the capacitor is charged up, we're going to have current that flows discharging the capacitor. And what's going to happen is the conventional current is now going to go this way, in the clockwise direction, through the resistor. And you might get a sense of what's going to happen. Initially, initially this capacitor looks like the battery, right? It has the voltmeter here would read the EMF of our original battery. So initially, the potential difference across the capacitor is just the EMF of the battery. But as the charge flows, as the capacitor discharges through the resistor, that EMF is going to decrease, and as it does, the amount of current going through the resistor is also going to decrease. I'm just realizing I made a mistake here, which maybe you caught. The initial charge on the capacitor isn't E over C, it's E times C. All right, so now what I might do, like we did before, is I could imagine making graphs here of I as a function of t, I as a function of t, and Q, the charge on the capacitor, also as a function of t. And I could imagine sketching what would this look like. So initially the current would be very large, right? Initially the current would be as though you had a battery of EMF E and just the resistor. So the initial charge here, the initial current would just be E over R. But then as the capacitor discharges, that potential difference decreases, and so too will the current. And so you're going to get this, or you might suspect you're going to get this exponential decay relationship again. And similarly, initially, the charge on the capacitor is that EC value, but it's going to diminish as it discharges. The total charge on the capacitor decreases. But since the current is decreasing, the rate at which the capacitor discharges will also decrease. So you're going to get a similar relationship of an exponential decay. So I'm not going to go through all of the details of how to calculate or how to come up with an equation. I'm going to leave you to do some of the dirty work here, but maybe we'll just say discharging the capacitor. And maybe I'll just note for us that the loop equation that you would have to start with, there is something slightly tricky about the loop equation you'd use. So I'm going to say the potential of the battery, that's Q over C, and I'm going to make it a positive this time. And the reason for that is since we're moving, if we go back in here, since we're moving in this direction, the clockwise direction, if you imagine a little positive charge, as it traverses the capacitor in this direction, it's going to, we imagine it's gaining a certain amount of potential rather than losing it, because it's going in the opposite direction. It's going against the electric field. So I'm going to make that positive, and then we would get minus IR equals 0. And I could write this Q over C minus dq dt. But here's the trick. The dq dt, the change, the rate of change of Q is itself going to be negative. So when I write I as dq dt, I need to put another negative in. dq dt times R equals 0. So the loop equation I'm going to use is Q over C plus dq dt times R equals 0. This is a little bit of an easier equation, but I'm going to leave you to solve it there to come up with, and again, you should come up with an equation in the form of exponential decay for Q, and the derivative of that would give you an exponential decay equation for I as well.